All right, good. Well, it's great to be here. It's really a pleasure to visit Loyola, and I've had a wonderful time. And I have fun giving this talk. I have fun giving this talk in part because I actually became a Catholic 9 years ago. After decades of reflection, not all of it deliberate, you look back and you think about, this was reflection, this wasn't. But I've been interested in this question of how science and religious faith interact with each other for much, much longer than that. And I am a professor in the astronomy department at Cornell. I lead one of the research centers there. I'm involved in a large number of NASA missions. And I also have had a lot of interactions with the Vatican Astronomy group, which you'll hear about in the second half of the talk. But I want to begin by giving you a kind of a prologue. Now, I look at most of the people here are pretty young, so maybe 20s. I think almost all of you have lived in a time when the words science and faith somehow look like they're opposed to each other. But it was really not the case for most of the history of science, even during the time of Galileo, when it was not a question of science and faith that opposed each other. And in fact, if you look at various editions of this very old book, Scientific Biographies of Prominent People, that's not the exact title, but you find that in the 18th century, about 1/3 of the scientists listed in that were actually religious, priests or brothers or nuns, whatever. And that number, of course, dwindled over time. And it's very small, so that we live in a time now where we think that these are either-or propositions. But even in the 19th century, mid-19th century, there were plenty of scientists who were very upfront about their religious faith, and one of those shown here by example is Louis Pasteur, famous scientist, of course, who developed pasteurization, who discovered that molecular forms can have left and right-handed versions. And he wrote that posterity will one day laugh at the foolishness of the modern materialist philosophers, the ones you called people who adhere to scientism or naturalism. So he wasn't right about that, although maybe that'll happen in the future. But he wrote that the more I study nature, the more I stand amazed at the work of the Creator. And Pasteur went on to say that he prayed in the laboratory as he worked. So very, very different from the point of view today. If you look at discussions of science and faith today on the internet, they're more like a kind of a WPW or Lucha Libre wrestling match. Now, don't get me wrong, I was always a fan of Lucha Libre wrestling as a kid, but this is probably not the right way to carry on an informed discussion, but that's what you tend to get on the internet. Basically, people drop-kicking each other over the subject of whether there is a God and whether science can answer everything and so on. I have always thought that the best way to understand the connections between science and faith and the way that people essentially individually address these two sides of their work is through looking at people who very, very evidently have lived lives of both science and faith. And so in Roman Catholicism, those would be religious who were also scientists. And so I'm going to profile one of them, Georges Lemaître, who was a Belgian Catholic priest who's also the father of the Big Bang model of the origin of the universe, the best and in many ways the only model we have of how our universe began. He's really a remarkable individual, and I'll only be able to cover certain aspects of his life. I understand that many of you have been taking astronomy, and how many in the audience would that be? Okay. How many of you have heard of Georges Lemaître? All right, well, I'm covering new territory, which is great. So let me give you a brief biography of him. This crowd is probably too young to have appreciated the 1960s Superman TV series, long before the movies. One of the things I like about Lemaître, which has nothing to do with his scientific accomplishments, is he seems to me a dead ringer for Clark Kent in the Superman TV series of the 60s. Looks like George Reeves and his Clark Kent guys. Actually, later in his life, he gained quite a bit of weight, as we all do, and didn't quite look the same. But anyway, he was born in 1894 in Belgium. He wrote that he was called both to the priesthood and to science at a relatively early age. He was educated at a Jesuit high school. Yay. All right. But he didn't become a Jesuit. Did not become a Jesuit. He got a bachelor's in mechanical engineering. He got his first PhD in math at the University of Louvain in Belgium in 1920, so almost 100 years ago. And that was summa cum laude, so his grades were obviously great. He was then ordained 3 years later a Roman Catholic priest, and rather than undertake pastoral work, he asked for permission from his superiors to pursue further studies in the United States, where he enrolled at MIT and got a second PhD in physics from MIT in 1927. Now, it's pretty big stuff to just get one PhD in the sciences, but this guy had two of them. And he had two of them by the time he was 33 years old, essentially, which is pretty good. So he was immediately hired as a professor at the Catholic University of Louvain back in Belgium. And what I would call his miracle years in English was really the time between 1927 and the mid-1930s when he published all of his really important cosmology work. And now there is a kind of a stereotype of scientists like this, that they do their best work in their 20s and 30s and then they burn out. In his case, it was partly that, and it was partly, as I'll describe later, some of the pressure associated with advocating the Big Bang model against a number of very formidable opponents, some of whom actually used his religious profession against him, and we'll talk a little bit about that. But in 1934, after all this remarkable work, he was given the Franqui Prize, the highest scientific prize in Belgium, and his nominator was Albert Einstein. Who has heard of Albert Einstein? Who has not heard of Albert Einstein? Okay, good. And he then was elected to the Pontifical Academy of Sciences in 1936. Pontifical Academy is an elected organization of top scientists from around the world. It is a component of the Vatican. And what's interesting about it is the scientists who are elected are not all Catholics. They're elected on the basis of their science. So some are atheists, some are agnostic, some are Jewish. It just depends on your research, not anything else. And in fact, Stephen Hawking is a member of the Pontifical Academy. Lemaitre became the president of the Pontifical Academy in 1960. At that time, Pope John XXIII named him prelate in the papal household. 4 years later, he retired from teaching in 1964. By that point, he would have been 70 years old, and he died in Belgium about 2 years later. So what I want to do is tell you about the important work that he did that leads us to say that he's really the father of the Big Bang, and then tell you about some of the things he had to go through after he did publish this idea, and how this interacted with the other part of his personality, which was the religious part as a Catholic priest. So I have to set the stage for you, and I understand those of you taking astronomy understand from your professor that you haven't done cosmology yet, so there will not be a quiz on this next Tuesday. It'll wait. All right. So what was the situation at the time that Lemaitre was doing his work? A little bit before that, the decade before Lemaitre went to graduate school, Albert Einstein published his general theory of relativity, which was really a theory of gravitation and how gravity worked. General relativity said that material objects, masses, distort the fabric of space and time in such a way that things, even light rays, for example, will not move in straight lines in space because of material things. And Einstein produced a set of equations that describe the behavior of space and time and matter in the presence of material objects and also of energy fields. Now, at the time that Einstein did this, in the second decade of the 20th century, literally about 100 years ago, in fact, we're celebrating the 100th anniversary, I think, of the theory. The astronomy of that time was really not very good. So, for example, I think those of you who've taken astronomy now know that our Milky Way galaxy, which is an assemblage of 200 billion stars, is just one of an innumerable number of other galaxies in the cosmos. Back in the 19-teens, 100 years ago, that was really not known. People could take images of spiral galaxies like Andromeda, here's one from the 1890s, but they couldn't really tell how far away they were. And it wasn't clear whether these were big collections of stars like the Milky Way or just clouds of gas that were in our own galaxy. In fact, they were called not galaxies or spiral galaxies, they were called spiral nebulae or spiral clouds. And so many astronomers at the time thought that it was entirely possible that the Milky Way galaxy, which now we know to be just an incredibly small part of our universe, was the whole universe. And everything that could be seen through a telescope was in that Milky Way galaxy. That implied, in turn, that the universe could be static and infinite in time, because there was nothing about these observations that suggested any kind of evolution. You know, there were the stars, there was the Milky Way. People didn't even understand how the stars generated their energy at the time. For all they knew, it was hanging up there in the heavens like that forever. And that was actually what Albert Einstein assumed. So when he applied his equations of relativity to the static universe that he thought was there, he immediately had a problem. And the problem was that the matter of the Milky Way galaxy would distort space around it, the space of this empty cosmos, empty except for the Milky Way. And as a result, space would collapse on itself. The universe couldn't be infinite and static. It would simply collapse because of the matter in our galaxy. And so at that point, Einstein, in order to prevent that embarrassment from his theory, invented something he called the cosmological constant. Who has heard of the cosmological constant? Who has seen the Big Bang Theory on TV? Okay, good. That's just a fidelity check there, if you're listening. The cosmological constant was a kind of a fudge factor in the equations that pushed back against gravity and allowed everything to be suspended in the heavens as long as you wanted. Some of you may have heard that Einstein regarded the cosmological constant as his greatest mistake. That isn't quite true, but he didn't like it because it was a fudge factor, and it kind of screwed up the elegance of his theory. But around the same time, other mathematicians, in particular in Russia, Alexander Friedmann, and there's a typo here, he spelled his name with two N's, not one, and then later Lemaitre, resolved Einstein's equations, assuming that the universe was expanding. Friedmann did it because he was a mathematician who was interested in just doing all sorts of different models. He had collapsing universes, static universes, expanding universes, universes that looked like pretzels. He was just a mathematician. And he did that in 1922, and he died in 1925 with very few people, except for Einstein, knowing about what he did. Remember, there was no internet in 1925, so if you published in an obscure journal, people wouldn't know what you were doing. So independent of that work, Lemaitre went ahead and also resolved Einstein's equations for an expanding universe. And he did it because by the time the 1920s rolled around, astronomers began to realize, because there were better telescopes, that the Andromeda galaxy and others like it, they really were not nebulae within our galaxy. They really were galaxies beyond our own, and that the universe was vastly larger than what people had assumed before. And so you could entertain an expanding universe, and in fact, at that point, astronomers were beginning to collect data that I'll describe the nature of in a few minutes, actually showing that galaxies were receding away from each other. So Lemaitre did this work, and just to kind of summarize that long monologue, actually Lemaitre met Einstein in the 1930s in the US, and this was not the actual dialogue, but it seems to fit. Einstein thought the universe was static and he needed a cosmological constant to prevent his relativity theory from collapsing all of reality on top of itself. But Lemaitre said, no, it's okay. Your equations allow for an expanding universe. Einstein actually didn't like that. In fact, at the end of one of Lemaitre's talks, Einstein apparently stood up and said, your mathematics is wonderful, but your physics is horrendous, meaning that he didn't accept the expanding universe. So Lemaitre went on, though, and he actually confronted the data. And he compared the data with his solutions to relativity. And he actually was able to conclude that galaxies were moving away from us at a speed that was proportional to their distance. Now, what kind of data allowed him to say that? Well, number one, by the 1920s, it became possible to get crude measures of the distances to other galaxies, basically by assuming that certain classes of stars in other galaxies would have a typical brightness similar to those in our own galaxy, and by seeing how much dimmer they looked, you could kind of estimate the distance to those galaxies. So that was number one. Number two, it was possible now with bigger telescopes to measure what's called the spectrum of a galaxy. Now, those of you who are taking astronomy, have you done spectra yet?
We do it in the spring.
Oh, the spring. I can't wait for the spring myself, but all right, doing it in the spring. Okay, so what is a spectrum? A spectrum is simply a kind of a chart of the brightness of an object, like a star or a galaxy, as a function of wavelength or color. The wavelength of light we perceive with our eyes is color. Things are brighter or dimmer at different wavelengths, and that's a spectrum, if you display it in a digital way rather than a sort of a analog way with colors. So galaxies are made of stars, and stars have very distinctive spectra that reflect their chemical composition. And astronomers, mostly in the United States, and this will be important in a minute, were making these spectra of galaxies, and they were noticing that some galaxies had patterns like other galaxies, but they were shifted. The pattern was shifted to the red part of the spectrum. It was all being slid over to longer wavelengths. And one interpretation of this, which was the interpretation that Lemaitre and others had made, was that these spectra were being Doppler shifted, that these galaxies were moving away from us, and as they were moving away, their light was shifted toward the red, the wavelength of light. Now, they weren't shifted because the galaxies were moving through a kind of a big void. They were shifting for a different reason, which is shown on the next slide. And that is that space itself was expanding. And this was the important inference that Lemaitre actually made that allowed him to derive the Big Bang model. So if you imagine the universe as a rubber band, and you draw a wave on it. This might be a wave of light coming from a galaxy. And now with your fingers, you pull the rubber band apart. What's going to happen? The wave is going to look longer. It's going to look stretched out, which means the wavelength is longer, which means the light is shifted toward the red, because longer wavelengths are toward the red. And in fact, if you imagine space itself expanding, if you think about this for a while, and if it's hard to think about it, you can actually do it by imagining space as the surface of a balloon and putting dots on the balloon and then inflating it. The farther away the galaxy is, the faster it's moving away from you. That's not necessarily the case if galaxies are just flying through a fixed space, but if space itself is expanding, then the farther away you are, a given amount of time involved in the expansion means that that galaxy has moved farther from you than a galaxy that's closer to you in this flow of space. And so the farther away the galaxy is, the more the redshift should become evident. And that was what astronomers were seeing in their data. Now, Lemaitre actually published this relationship based on the astronomical data and based on this relativistic solution, Einstein's equations. In 1927, in a Belgian journal, Annals of the Scientific Society of Brussels, published in French. Now, French is a beautiful language, but it was not the language of astronomy at the time. And neither was German, which was still kind of the lead language in physics and chemistry. because the big telescopes were being built in the United States, and Yerkes Observatory near, up in Wisconsin is one example of that. The language was English, and the journals were either British or American. So Lemaître published this monumental work in French in a Belgian journal in 1927, which nobody read. And in 1927, remember that you couldn't get on your laptop and Google on Expanding Universe Lemaître Belgian Journal, and it would come up. It wouldn't come up because the internet didn't exist, okay? So if you didn't happen to subscribe as an American or British astronomer to a French-Belgian journal, you didn't see it, which most people didn't. And that's key, because one of the American astronomers who was collecting these data, Edwin Hubble, published exactly the same relationship, not knowing what Lemaître had done, in 1929, 2 years later, and he published that the speed of a galaxy is just the distance the galaxy multiplied by a constant. That constant became known as the Hubble constant for Hubble. Cheery guy, isn't he? And then this very famous space telescope that's been operating for more than 20 years, long after Hubble's death, became known as the Hubble Space Telescope. If Lemaître had published in an English language journal, it might be that this constant would be labeled L and would be the Lemaître constant. And this telescope might be the Lemaître Space Telescope, but it wasn't. So what was interesting, though, is that this paper by Lemaître did come out in English, as you can see here, in 1931. He was urged by his colleagues, after Hubble published his results in 29, 2 years after Lemaître's, to republish in an English language journal, which Lemaître did in the monthly notices of the Royal Astronomical Society. But the equations that demonstrate that he had worked out this Hubble relation were omitted from the English translation. And for years, there were all these theories about diabolical conspiracies against priests and so on by the editors of monthly notices. Turns out, actually, an astronomer, Space Telescope Science Institute, found some correspondence between Lemaître and the journal, which had been lost or filed away somewhere. It was Lemaître who omitted those equations. And he did that because by that point Hubble had published them, and Lemaître, in his letter to the editors, said, I have omitted these equations because they have already been published by Hubble and there's no reason to put them in again. Now, those of you who are undergraduates probably don't know the typical behavior of us professors who do research, right? We're stepping on each other's heads to publish stuff to make sure that we're the ones who have priority and not the other guys. So this was a remarkable piece of modesty on the part of Lemaître to not publish it because Hubble had already done it. Nonetheless, Lemaître gets credit because Hubble actually didn't understand the implications of his work. What's very interesting is that Hubble actually was never in favor of an expanding universe, and he was absolutely opposed to this Big Bang idea that the universe had a fixed beginning. And in fact, Way and Nussbaum, in a Physics Today article, said that Hubble never came out in favor of an expanding universe. He doubted it to the end of his days. You can find on the web a newspaper article from 1941 from a Pasadena newspaper. And the savant in that headline is Edwin Hubble, refuting the theory of the exploding universe that came from his own data. So he kind of took himself out of the picture as a consequence of that, even though most astronomers don't realize that. And it was really Lemaître who was the first to combine the theory, the relativity, with the observational arguments to show that we live in an expanding universe. But again, as Bob Kirshner, an astrophysicist at Harvard, points out, Lemaître was simply severely underrated because of where he published. Now that would be the end of the story were it not for the fact that Lemaître went on. And he, knowing the data that he had, knowing that space was expanding, knowing that he could calculate the rate at which these things were happening, he reasoned that the universe actually had to start a finite amount of time ago, that this expansion couldn't have sort of slowed and so on, so that the universe had a kind of an infinite lifetime to it, the universe had a beginning a finite amount of time ago. And he published this in 1931, and thankfully he published it in English. Are those pigeons? Or is this thermal contraction? Oh, okay. Well, lecturing in a greenhouse has its interesting twists. So he published this, thankfully now, in an English language journal, well-known, called Nature. And the article was entitled The Beginning of the World from the Point of View of Quantum Theory. And in this article, Lemaitre said, the universe began in an incredibly hot, incredibly dense state that was so compressed and so hot that the physical laws we have today weren't applicable. And he didn't call this the Big Bang model, he called this the primeval atom model. The Big Bang came later. I'll explain how that term came up. As one of his biographers, Craig, says, it was a short article, that's it, you see it there, one column, a visionary piece of cosmopoetry. Every bit of it is understandable. There's some remarkable tidbits in here. I show you one part where Lemaitre uses his model and quantum mechanics to argue that the world was not predetermined in its evolution, that the principle of what he called indeterminacy from quantum mechanics, which, by the way, he accepted and Einstein didn't, meant that the evolution of the world happened in an unpredictable, step-by-step way, essentially free will. An idea now actually that's used by atheists to argue against creation of the universe by God, but actually that's not a valid argument. Lemaitre was using it just simply based on quantum mechanics, and he believed in God. So there are all sorts of interesting tidbits here in this article. But with respect to the subject of God, here's the Big Bang model. We start out with this incredibly compressed, incredibly hot something. It begins to expand. Space expands. It cools. Galaxies form. Astronomers of the time, most of them, really hated this model because it required that something get the universe going. That there was a point, you can't even call it in time, at which what we see today didn't exist. And that, for many, was simply kind of a hidden code for saying that God created the heavens and the earth. And because Lemaitre was a Catholic priest, many of these astronomers said, aha, we know why he put that model together. So is God sitting here at this point? Actually, if you're a Thomistic philosopher, where would you say God is? God is creating all of this all the time, right? But anyway, the astronomers were saying, aha, it's all down here at the beginning. Lemaitre is pushing this idea because of his religious background. But Lemaitre, in fact, said that that's ridiculous. He very, very clearly laid out that the Big Bang model, in his view, and this is a quote from 1958 from a physics conference in Solvay, that this model remained outside any metaphysical or religious question, to quote him. It leaves the materialist free to deny any transcendental being. So in his public persona, Lemaitre was saying, it doesn't matter what physical model you have, it doesn't say anything about God. Remember that, because we'll come back to that in a minute. Lemaitre was also very firm in his assertion that the Bible was not a literal depiction of the history of the universe and of the earth, that it was given to us for a different reason. And in 1933, I'll read this in its entirety, he said, the writers of the Bible were illuminated more or less on the question of salvation. On other questions, they were as wise or ignorant as their generation. The idea that because they were right in the doctrine of immortality and salvation, they must also be right on all other subjects is simply the fallacy of people who have an incomplete understanding of why the Bible was given to us at all. Harsh words, but he was very firm about this and said this many times in different ways throughout his career. So he was, a very Orthodox Roman Catholic priest, Orthodox in his views, but very firm about, what was and wasn't the purpose of the Bible and what was in there. Now, all this would be great, but as we all know, sometimes popes come along and they stir things up. And in this case, it was Pope Pius XII who was a brilliant man who was very intellectually very astute and very interested in science and technology, and was fascinated by this primeval atom model. So fascinated that he wrote some stirring words about it. Those stirring words were that the Big Bang, what we call the Big Bang today, proved that God created the heavens and the earth. Exactly what Lemaitre did not want people to conclude from the model. And in fact, Pope Pius said this in a famous speech to the Pontifical Academy of Sciences in 1951 with Lemaitre in the audience, not knowing what was about to be said. And the Pope said in part, I'll read only part of this, "Present-day science has succeeded in bearing witness to the august instant of the primordial fiat lux, let there be light. When along with matter there burst forth from nothing a sea of light and radiation, and the elements split and churned and formed into millions of galaxies." It's beautiful. You know, the Pope wrote as beautiful a popular science explanation as you would get from Carl Sagan or anyone else. Perfect. He then goes on to say, hence creation took place. We say, therefore, there is a creator, therefore God exists. A student in one of Lemaitre's classes reported that Lemaitre came back from that Pontifical Academy meeting in the darkest mood he had ever seen his professor in, because he realized that if this were associated with his model, people would say, aha, a priest put this model together on the basis of a religious predilection, and so the model is just not valid as a piece of science, and that's not what Lemaitre wanted. So he became even more alarmed when he was told that the Holy Father was about to deliver a speech not merely to the Pontifical Academy of Sciences, but to the 8th General Assembly of the International Astronomical Union, which is the largest organization of professional astronomers that happened to be meeting in Rome later that year. And of course, Lemaitre thought, he's going to say the same thing to this group, and my model's finished. So he actually flew to Rome on the way to another meeting. He talked with the then president of the Vatican, of the Pontifical Academy, as well as to the Cardinal Secretary of State, and pleaded with them to talk to the Holy Father and say, please don't say these things for reasons X, Y, and Z. We don't know what X, Y, and Z were. They did that, and Pope Pius XII said, okay, I won't, and he didn't, and that was the end of it. But it wasn't the end of it, because these things had already been said. And so the Big Bang model came under a kind of a cloud. And this was 1951. In the 1940s, 3 other astronomers by the names of, actually Tommy Gould's on the left, Herman Bondi in the center, and Fred Hoyle on the right. Fred Hoyle, famous astronomer who was knighted by the Queen a little bit later, and had his own BBC radio show and had all sorts of interesting ideas. Tommy Gould founded the modern Department of Astronomy and the center that I direct today in 1959, so there's a connection there. They came up with a completely different model of the universe that preserved the infinite nature of it, that basically eliminated the need for a creator. The story is they did this while watching a horror movie at a theater, a movie theater, in which in the plot the time loops around and the unfortunate characters are always caught in the same situation again and again and again. And they said, hey, let's do this with the universe. So what did they do? Well, remember, space is expanding. Galaxies are flying apart from each other, so matter is getting more and more dilute. So what they said is, what if matter was being created somehow in the empty spaces left behind by the stuff that has expanded away? Sounds pretty arbitrary. But if you actually calculate how much material you have to create, and I have my class, upper undergraduate class do this, in every square meter of space, you only have to create 2 protons, 2 hydrogen nuclei, every 10 billion years. So something the size of this table here, every 10 billion years, 2 protons would pop into view. Now, can you test that? Of course not. It's a ridiculous amount of time. So the model seemed viable. But more than that, Fred Hoyle was a master communicator and very ardently anti-religious and also anti-communist. He managed to put both of his dislikes in one quote, both Catholics and communists argue by dogma, he said. But more importantly, he had this BBC science radio show. And in order to lampoon the primordial atom model and its creator, Lemaitre, he referred to the model as a Big Bang. He was the one who made that up. And he referred to Lemaitre as that Big Bang man. And when he would see Lemaitre at conferences, in at least one case, Hoyle was sitting with a colleague, Lemaitre came into the room, and Hoyle said in a loud voice, "Oh, there goes that Big Bang man." So this is sort of the 1950s equivalent of cyberbullying, if you want to think of it that way. And actually, it bothered Lemaitre immensely. He actually had nothing personal against Fred Hoyle, and likewise, they actually liked each other, and apparently they went vacationing with Fred Hoyle's wife in the Italian Alps one time for a week, incredibly. But they were opposed like this in terms of religion and their science. And it is thought by some biographers that a lot of this, let's call it pre-internet cyberbullying, dissuaded Lemaitre from working further on his model. At a time when people were beginning to think of ways to prove or disprove the Big Bang or the steady-state model. So he missed out on that in the 1950s. But one of those ways actually did pan out, and it was thought up by other scientists, and that was the following. If you imagine this model, we'll go from calling it the primeval atom to the Big Bang model now, because we've been through Hoyle. Everything starts out really, really hot and really, really dense. And when space expands and matter goes with it, it's so hot that everything is charged. The electrons are separate from the protons. It's what physicists would call a plasma. And in a plasma, light can't travel because it keeps getting absorbed by these electrically charged particles. And so space is completely opaque. Eventually you get to a point where the universe becomes dilute enough and cool enough that the electrons can combine with the protons, that you no longer have a charge. Matter becomes neutral and space becomes transparent. If you prefer the version of the book of Genesis, the light is separated from the darkness. At the point at which that happens, light is free to move through space. Prior to that point, light was intermixed with all the matter and couldn't move through space. And so there's a screen, a kind of a glowing screen in this expanding flow of space, which is the point at which the light became free to move. And that happened in modern models about 380,000 years after the Big Bang, very soon after the Big Bang, at a temperature of about 20,000 degrees Kelvin. That's where things start to become neutral. But remember, the flow of space is such that the more distant things are, the faster they're moving away from you. The faster they're moving away means the more redshift you have. And so this was a very early phase of the universe. So it's redshifted so much that the wavelengths of light are stretched out from what you would expect for something at 20,000 degrees Kelvin to something that is glowing at only 3 degrees Kelvin, 3 degrees above absolute zero. And the only way to see that is to observe in the radio part of the spectrum, because something that cold predominantly radiates in the radio. So this was the prediction, and along come Penzias and Wilson, two radio engineers working at Bell Labs in New Jersey, designing what this looks like a preposterous flying machine. It's actually a radio telescope. And that radio telescope was very sensitive, and it detected this background radiation. Initially, they thought it was noise. Then they realized what it was. And this demonstrated that the Big Bang model was correct and the steady-state model was wrong, because in the steady-state model, nothing changes ever, so there can't be a point where the light gets separated from the darkness. And to his credit, Fred Hoyle almost immediately admitted that the steady-state model had to be disposed of. This happened, luckily, just months before Lemaitre died. So he learned that his model was correct in the end. Now let's go back to the question of God and the Big Bang and Lemaitre's assertion that this doesn't really mean anything in terms of the existence of God. That was certainly his public position, but it apparently wasn't his private position. Lunine, a historian, has found in archives at Louvain an early manuscript of that 1931 paper. And in that 1931 manuscript, the paper to Nature, there's an extra paragraph at the end, which has been crossed out with a pen, and what it says, and I'll read it, is, "I think that everyone who believes in a supreme being supporting every being and every acting," he was French, so he probably meant action, "believes also that God is essentially hidden and may be glad to see how present physics provides a veil hiding the creation." So Lemaitre was thinking about the theological implications of his model. He really was, and initially he thought to put this statement in his Nature paper, and then he obviously thought better of it and decided not to do it. But clearly he was not doing what Stephen Jay Gould called non-overlapping magisteria. He was not separating his science and his faith in his own mind. He was thinking about the implications of it. Furthermore, if you read the first part of this 1931 paper, and you have read some of St. Augustine's work, you find there's a remarkable resemblance in a very interesting way. So this is the beginning of that Nature paper. And the first sentence I've shown here says, "If the world has begun with a single quantum, the single primordial atom so hot, so dense, that physical laws don't yet apply to it, as we know them, then the notions of space and time would altogether fail to have any meaning at the beginning. They would only begin to have a sensible meaning when the original quantum, this original primeval atom, had been divided into a sufficient number of quanta." So if there's just one thing and nothing is moving, then there's no sense of time, and maybe no sense of space either. So remember that statement. And the second statement, just a half a sentence later, is, "The beginning of the world happened a little before the beginning of space and time." So with the Big Bang came time. So if you ask what was before the Big Bang, that's not a valid question to ask. So now let's go to Augustine and The City of God, Book 9. And Augustine writes, "For if eternity and time are rightly distinguished by the fact that time does not exist without some movement and transition, while in eternity there is no change, who does not see that there could have been no time had not some creature," just substitute for creature the word quantum, "been made by which some motion could give birth to change?" So without things interacting with each other, there is no time, and there is no space. So it's really the same idea that Lemaitre wrote 15 centuries later. And then the second point that Augustine makes a little later is, "Thus assuredly the world was made not in time, but simultaneously with time." Lemaitre writes a little after, but there's no difference between them. These are the same ideas expressed in almost the same way. Lemaitre was educated in a Jesuit high school. He had to have read The City of God. Had to be there in his mind somewhere. Whether he ever admitted that, I don't know. So to close on him, and I'll spend 5 minutes on the Vatican astronomers, Lemaitre in this period did so many other things. He wrote papers that really presaged a lot of modern ideas on dark energy, which is this mysterious force that accelerates the universe, a lot of which people don't recognize and don't appreciate. In fact, a somewhat younger contemporary of his many years later, Sir William McCrae, who was certainly not a friend of religion or anything like that, said, "Lemaitre was a scientist of superbly robust common sense. All of us who knew him must ever have wished we had paid attention to his ideas," that dry British humor. I think a lot of this was this battle that Lemaitre had with the steady-state models, and what ended up being inadvertently, because of what Pope Pius had written, sort of a battle between science and religion. Another physicist at the time who helped come up with this background static idea, George Gamow, who identified as an atheist, always used to make fun of the fact that the Pope had said these things. So unfortunately that got lost, but I think today a lot of astronomers are coming back to realize the importance of Lemaitre's contributions. Now I'm supposed to talk for only 50 minutes, right? So let me finish in the last 5 minutes and talk about astronomers of today who are also religious. These are the Vatican astronomers. The Vatican Observatory was founded 125 years ago by Pope Leo XIII. Actually, astronomers have been working for the Church for centuries, since Pope Gregory established the Committee to Reform the Calendar System back in the late 1500s, he had a mathematician astronomer on that committee, and the Jesuit astronomers then interacted with Galileo and so on. But the modern version of the observatory was set up 125 years ago for political reasons that may not be quite so interesting to this crowd. These are all priests and brothers, all Jesuit except for one who's a parish priest in Rome. Some of them are shown here on the right. The director, Guy Consolmagno, is a Jesuit brother, a planetary scientist like me. I knew him when he was a postdoc before he became a Jesuit back in the early 80s. Wonderful guy with a wonderful sense of humor. And they do their research, and they also work as priests and brothers. So when I was living in Rome, I went to a church in Aricia near where they lived. That's where I would go to Mass. And one day I went to confession. Nothing serious, don't worry. The way they did confession in Italy is they start the Mass and you could sneak off into the back and do the confession and sneak back. So I snuck off into the back. And there, in front of me, hearing the confessions, because they didn't use a screen, was Gabriele Giunti, one of the Vatican astronomers working on general relativity and also hearing confessions at this church in Aricia. The harmony of the way that science and faith is combined in these individuals in such a quiet way always impressed me. And I lived with them for 3 months, and I was always impressed, and so is the astronomical community. So George Coyne, former director of the Vatican Observatory, who's now teaching at Lemoyne College, was given by the American Astronomical Society the George Van Biesbroek Award, a very prominent award in 2010 for the summer schools for graduate students that the Vatican astronomers sponsor every 2 years. And Guy Consolmagno was awarded by the division of that astronomical society, the Division of Planetary Science, the Carl Sagan Medal in 2014, which is for communication of science with the public. But the citation specifically referred to Guy's ability to demonstrate the harmony between science and faith. And this is a statement by a secular member organization of professional astronomers. Guy actually was elected to be the chair of this division of planetary science a few years before that. So there's certainly harmony there. Here are some of the students of one of the Vatican summer schools and an audience with Pope Francis. There's Guy with the Vatican Meteorite Collection. The observatory now they don't observe from Rome. The skies are too polluted with light. They have a very novel advanced technology telescope that they built in the late 80s, early 90s near Tucson, east of Tucson, actually, in the mountains. So there's certainly harmony there. Now, these are all religious, okay? People who are priests and brothers and sisters and so on. How does that apply to us lay astronomers? Well, it's more difficult in the secular world because we encounter colleagues who are either diffident or actively opposed to religious ideas, and it's particularly hard for students. So a group of us have put together an organization called the Society of Catholic Scientists. There's our website. The purpose of it is to foster harmony among foster fellowship among Catholic scientists, to witness to the harmony between the vocation of science and the life of faith, to be a forum for reflection upon and discussion of questions concerning the relation of science and Catholic faith. We have 130 members. We put this together in coordination with the Archdiocese of Philadelphia, and we are very much trying not to be the guy in the orange tights in that lucha libre wrestling thing. We're not an advocacy group. We are trying to demonstrate harmony between science and faith among lay scientists who happen to be Catholic, and that's the purpose. Here's our board of directors. I'm the vice president. Stephen Barr, professor of physics at Delaware, is the president. You see here biologists, astronomers, and physicists, and more. So we'll see how we do. So let me close. And by the way, we're going to have a student membership category so that students can participate in some of what we're doing. I'm happy to talk about our planned activities, the first of which is a gold mass for scientists at MIT on November 15th, which will be celebrated by one of our board members, Father Nicanor Austriaco. Let me close with some final observations. it's very easy to sort of do one of three things that are not good. That you happen to have faith, and so you think you can't be a scientist. Wrong, but I've heard that from some high school students. Or you become a scientist, and so you think you have to give up your faith. Nope, that's not a good thing to do either. Or you separate the two, the non-overlapping magisteria. That's kind of a cop-out as well. I mean, sure, you do your science without having your ideas about God enter into the specifics of the experiments you're doing. But it's important to recognize that these two parts of you will always be combined in some way. And Father Tanzela Niti, who's a theologian and astronomer, said it very well when, actually this is the older version of my talk, not the new one. So I put a different quote in here in which he said that the heavens and the earth that were created by God are the same heavens and the earth that are studied by science. And so science and faith can never be separate in any individual human being. But when you're a plumber, you fix the plumbing without thinking necessarily about God. And that's the way we do science, but we can step back and contemplate after that. Secondly, from Faith and Reason by Pope John Paul II, St. John Paul II now, it is faith which stirs reason to run risks so that it may attain whatever is beautiful, good, and true. So faith, in whatever form you have it, either religious or something else, in many ways motivates science. And it's fair to say that the Judeo-Christian point of view of the world almost certainly energized science in the way that we practice it today. That's another whole talk which can be given. So, and faith without works is dead. So you have faith, you need to bring it out into the world. Part of that, if you're a scientist or want to be a scientist, is to show how these two are harmonious with each other and not in conflict. That's a responsibility that we have as scientists who happen to have faith. So, went to retreat recently. A young man who was on a hike with me, who's not a scientist, looked at me and said, "So, Catholic scientist, how does that work?" I couldn't show him all the slides in this talk while we were hiking, but that's how it works. And so, yes, you can be a great scientist, and you can be a faithful practicing Catholic, or Muslim, or Jew, or Hindu, or Buddhist, or whatever. But you just have to be prepared to explain that and to defend that to others, and by doing so, you not only push this debate back to where it needs to be in a more reasoned sense, but you also give greater glory to God in doing both. So thank you very much.